In the last class, two questions remained. One was, one of you asked the question that when I was talking about the density function, the probability density function, and said that you can obtain the average, you can obtain the mean square from the probability density function by the following expression is equal to integral of the whole range. So, x p x dx integrated over the whole range minus infinity to infinity. This gives you the mean value. The question was that, who was the question? He is absent today. Someone, one of you asked that this will have the dimension of x square. This will actually not, because the way the Px has been defined, the probability of finding the state x within a certain range is given as integral of x1 to x2, the range Px, which means that over the whole possible range this quantity will yield 1, because what is the probability of the state lying between minus infinity to plus infinity? It is 1. It has to be inside that range. So, this integral yields 1 over the whole range. Over a smaller range, it yields a number that is smaller than 1. Now, in general, the Px would be a continuous function. For example, you might say the Px is a function something like this, which means say this is 0 and this is say some number, say 1. So, that for different values of x, it takes different probabilities and the area under this curve is 1. Now, when we do this, what exactly do we do? Oh, there is another way of looking at it. Suppose I want to find the average of some function, like say sin square x plus something, some function of x, and say I am asking what will be the average value. So, there is a random process going on giving me the variable x. Now, what will be the average value of this term? In the first go, it looks very formidable problem, but actually once you have the probability distribution function, it is no longer a very difficult problem, because all you need to do is, for every value of x, you multiply this by the probability, integrate over the whole range, and that is it. So, all you need to do is to integrate this times Px, it will yield. So, that is one of the strengths of having the probability density function measured. Now, in this case, what are we doing? Imagine, for the sake of our understanding, that this is not a continuous spectrum, not a continuous probability spectrum, it takes specific values. So, what is the probability of taking this value? This much. What is the probability of taking this value? This much. What is the probability of taking this value? This much, so on and so forth. Suppose it is given like this, then what would this imply? It implies that take this value of x times this amount of probability. This probability is a number smaller than 1. So, you get something times 1, something times x, plus this value of x times this probability plus this. So, you will notice that what it is yielding after all this summation has a dimension of x, right. That is why what it actually yields has the dimension of x, not x square. Clear? The second question actually pertained to the way we were writing the power spectral density. We said the power spectral density is x f, okay, and then in the process of obtaining the theorem that we proved that day, what did we say? We said, do we have the pages there? Should be somewhere. Yes, it is here. See, we had written it as xf square, the power spectral density as xf times xf. Now, this is true only if xf is a real number. If it is complex, then it would not be valid. True. So, yesterday we did it basically under the special condition where the Fourier transform of x yields a real number, but that would not be the general case, of course. So, in the general case, how would we go about it? We will say that this is equal to into, right, where this is the complex conjugate of this fellow, and then we have to go ahead with this formulation. So, what actually did we do? Our line of argument. Okay, look at the line of argument that we used in the last class. We said that if you have two time functions xt and yt, if you take their convolution, then this is defined as this, fine, and there is a property that the convolution of two time variables is equivalent to the Fourier transform of their product, the product of their Fourier transforms. So, we had used this property, but now the difference will be that here, okay, I have to look for it. So, we will not look for it, we will substitute this. We have started from the equation minus infinity to infinity, we started from here. Now, we will have to write it as, we will have to write it at x f and x star f fine. We will have to write it like this. Okay. Then this term, see, we are again using this property. The product of their Fourier transforms, the product of their Fourier transform, if you take transform that, you get the convolution. So, we will have to do exactly the same way, but then we have to consider the situation, the inverse Fourier transform of xf is xt, all right. What is the inverse Fourier transform of x star f? X minus t. That is one of the theorems that you may have learned in while learning about the Fourier transform. So, essentially what you get out of it is x of t and this is convolution x minus t. Okay. Now, this convolution, if you write as the formula for convolution, you get minus infinity to infinity, this is x t times x minus t minus tau. All right. At this stage, let me only comment that under certain conditions, this is same as okay. That means x of minus time something is same as the x of plus the same time. That will be true under certain conditions. I will come to that. That means, under the condition that in a shift of time, the character of the time series does not change in a statistical sense. No, actually it will not be. The issue is that different books give different definitions of the this function, and some cases they take the t as a variable, some cases they take the tau.
Yes, sir, but the LHS is a function of t, and the RHS is not integrating over t, so it will be a function of tau.
LHS is a function of
T, xt, convolute x minus t.
yes.
And the RHS is basically integrated, it's integration over t. So ultimately it is a function of tau.
Oh, so you have to interchange these two. T and tau. Okay. I mean, you might as well interchange these two so that to bring in this form. Huh? So essentially, it is the same thing. What you call, I mean, it will not be different if you interchange t and tau. Now, so this is same as the autocorrelation function. Now, this obviously brings the question under what condition this can be written. If it cannot be written, we have some difficulty in writing like this. We will come to that question now. Now, the point is, so far we have been considering only one time series, a time series that is coming from some kind of a process going on. Now, in practical situations, there could be more than one time series available at the same time. That means, that would be called an ensemble of time series. So, one time series is coming like this, say, another coming, and third one like this, and so on and so forth. Now, what do these ensemble mean actually? You might imagine these as generated from the same process, or in other words, if you have in your mind something like the Lorentz equation which you have come across, the same Lorentz equation, but starting from different initial conditions. So, they will lead to different waveforms, and in that sense they would be different time series, and as a result you have a ensemble of time series. Now, there are various situations where it is convenient for us to have only one time series to be able to talk confidently about the character of the whole ensemble. In some situations, you have a finite length of an ensemble of time series, but you want to be able to talk about a large length of a single time series. What are the situations? One situation you have already come across. For example, while talking about the Frobenius-Perron operator, what was our essential logic? Our essential logic is that if you have an ensemble of series, their property under certain condition would be the same as the property of a single time series. Even if we cannot wait for an infinite amount of time to obtain the time series, we can still talk about the whole time series with confidence, but that happens under certain conditions. In order to understand those conditions, let us look at it this way. Suppose this is y, say I say 1 of t, this is y 2 of t, this is y 3 of t, and so on and so forth. I am putting brackets because otherwise it might look at y square and y cube, so that should not be confused. So, you have an ensemble of time series, and we are trying to understand its properties, the property of this ensemble. Now, we might say that I identify a particular time chunk, and we might say that now we have not a chunk, we may say that just a t1, say this is the time, and we might divide the whole range of the y, that means y is contained within a specific range, we might divide into small boxes, the way we have already done. Okay. So, say this particular box is y1 plus delta y1. So, here is y1 plus delta y1. Delta y1 is the length of the box. Okay. Then at time t1, we can count the number of the ensemble that fall within this box. Okay. Notice here we are counting across this, not counting across that. We are counting across the ensemble. That means we have identified a time and saying that, okay, out of the whole number, how many are there? Suppose m number is there. So, to total m number. M number of ensembles are there. So, out of the total m, say a small number n1 was within this range y1 plus delta y1. So, is n1. Okay. Then we might say the probability of finding a member of the ensemble in the range y1 to y1 plus delta y1 would be n1 by m at time t1. Okay. So, we say probability of y1 plus delta y1. So, y to fall within the range of y1 to delta y1, probability of that would be n1 by m. So far simple stuff. But now, if m is large, that means you have a large ensemble available, and we take very small delta y, then obviously we can calculate that for the whole range, and what does it yield? It yields a probability density function at time t1. Clear? So, if we take large value of m, that means large number of ensembles, and if we take small delta y, then it becomes small delta y means it becomes smoothed into a function, into a continuous function. And what does the continuous function then imply? It implies that at t1, what are the relative probabilities of finding a member of the ensemble at different values of y? Okay, but at t1, remember that. Likewise, we can calculate that at time t2, at times another time say t3, and so on and so forth. Is that clear? We can calculate a probability distribution function over the ensemble at specific times. Now, if this probability distribution function over the ensemble does not change in time, then the time series or the ensemble is called a stationary ensemble. Okay. So, this is the definition of something stationary, and if it changes with time, then it would be non-stationary. The easy way of visualizing when a time series will be stationary and when a time series will be non-stationary is, suppose you start from initial condition and attractor is here, and so after some initial oscillation or initial transient, it goes into the attractor. If you take the time series before it reaches the attractor, it will be non-stationary, it will change with time, but after it reaches the attractor, it will be stationary. But also the attractor could be a point attractor, a periodic attractor, a chaotic attractor, quasi-periodic attractor, all these possibilities are there. So, a stationary time series could be of all the different types. Now, if a time series is stationary, but its elements are not periodic, then it is called ergodic. Okay. So, ergodic means stationary okay. Why is this definition important? Because when we say that in some situations I may have a single time series over a long time, all right, but I want something of interest about the whole ensemble. In some situations I have a large number of ensemble available, but I want to infer something of interest about a long time series. Yes, those things, these two different concepts will be equal if a system is ergodic. Okay. So, that is why the importance of ergodicity comes, practical importance of ergodicity, that in some cases I want to infer something of interest about the average behavior of a system. For example, whichever initial condition I may start from, the average current flowing through an ammeter will be this much. These are very practical considerations. I want how much will be the deflection of the ammeter pointer. The actual current flowing through the ammeter coil would be a chaotic thing, but ultimately you will see something. How much is that? In order to calculate those, you need the concept of ergodicity. Clear? If a system is ergodic, that means it is stationary and non-periodic. Obviously, that will include within its fold quasi-periodic orbits, because quasi-periodic orbit is stationary. It has already reached the torus and it is moving inside the torus. So, obviously, it is stationary and it is also non-periodic, and that is why a quasi-periodic orbit is also ergodic. Not only the chaotic orbit, but also a quasi-periodic orbit is ergodic. There is an important thing associated with the concept of ergodicity, it is called mixing. It is called mixing. Suppose there is a state space, there is a chunk of the state space inside the attractor, and the attractor is ergodic. The moment I prove that it is ergodic, it immediately implies that starting from any initial condition, it will visit neighborhoods of every other point in the state space within that range. Is the point clear? That means, if I start from any point, I can target another point and I will reach there. With confidence I can say that I will reach there sometime or other. In one of the future classes, I will show you how to take advantage of this concept in practical conditions, practical problems. So, ergodicity is this, that there is mixing. The concept of ergodicity is used in, say, industrial processes, for example, where you want mixing. Say a chemical reaction is going on, you want proper fast chemical reaction, that means you want proper mixing of the states, and that can be ensured if you infuse ergodicity in the system. Essentially, it is done by infusing chaos in the system. Now, the torus, I told you about the motion on the torus. It could be a periodic orbit, it could be a quasi-periodic orbit, and you have understood that the quasi-periodic orbit is ergodic, but the periodic orbit is not. That is why in some literature, when you want to go back to books and want to study, you will find that in some cases, the periodic orbits occurring on a torus is called a resonance torus. That means, two frequencies are in resonance. It is called, that torus itself is called a resonance torus. And the situation where the two frequencies are incommensurate, as a result the periodic is the orbit is quasi periodic, it is ergodic. So, the torus is called a ergodic torus. So, remember these words, so that if you encounter these words in any literature, do not be confused. A ergodic torus means quasi periodicity, resonance torus means not just any periodic orbit, but periodic orbit happening on the surface of a torus, mode locked behavior. Now, refer back to this problem, you would immediately realize that these two are statistically true in stationary processes, ergodic processes. Okay. So, this particular theorem is particularly applicable to ergodic processes, chaotic processes, quasi periodic processes, where you want to use this in order to either obtain the autocorrelation function or you want to obtain the power spectral density. Clear? Fine. Let us come to another issue now, again related to time series. There are a huge number of situations, practical experimental situations, where it is only possible to place one probe in the system. Imagine that a chemical reaction is going on, that means there is a huge amount of things going on in different places, and there are adequately large number of state variables in the system. And if there is a mixture in the mixing the thing, there will be a motor. A motor means inductances, a motor means windings, motor means current, they are also state variables. So, there are huge number of state values in system, hopelessly large to observe all of them. Okay. Similarly, there are often situations where it is hopelessly inadequate to observe all the state variables. For example, say weather. How many state variables are there? Infinite. Or where you can at least say that it is a finite dimensional system, but there are too many state variables to observe. Say the power plant, a huge power plant, that means there will be something like 1,000 state variables, but you do observe. So, I am now setting up a situation where there is some kind of experiment, but logically speaking there would be a very large number of state variables, and if you want to model that, model say a convection process, say the process where slowly turbulence develops in a fluid, you need to really measure the state at every place, the motion, the pressure and stuff like that at every point, and ultimately then only you are able to write down some equation. To the So, in such situations where there are some state variables that you can possibly observe, but that is finite in number and less than the actual number of state variables that you can logically identify. One way to represent such systems would be to start from the basic first principles and try to write down the equations and try to develop the model. But in many cases that is a hopeless pursuit, because the system is so very complicated. Now, much of science has developed on the idea that even if we cannot write down the exact model, we can still mathematically represent this in terms of relatively simpler models. So, what often people do is, suppose you have got just one state variable coming and you have the time variable with x. Now, from it how much can we infer about the character of the system? The moment I say that, you would ask, what do you mean by the character of a system? Well, what do we really want to do by writing a model? What do we really want to do? We want to predict. If the system is doing such a thing now, what will it do say 10 seconds later? That is what we want to do. From this kind of a waveform, can we predict that? Say, I say I am here, I observe the variable value, say right now it is 0, and then can I predict what will happen say 1 second later? Obviously we cannot, because here also it is 0 and here also it is 0, and if this much is 1 second later, after that it went up, if this much is 1 second later, after that it went down, and therefore simply saying that the state value is 0, we cannot infer anything of interest. We cannot really say what it is going to do in the future. Scientists have especially the nonlinear dynamics people have formulated a extremely useful method of overcoming this problem. What they do is, it is not difficult to see that the difference between this point and that point. What is the difference? This point and that point. If we have it, if you plot it in a 2D state space, they will be seen as different. Because you have drawn it in 1D, you are not being able to distinguish them. So, you need to somehow draw a 2D state space. And here there is to be something, but the problem is that you have actually accessed only one variable, not two. So, how to construct the other variable? The nice way is what is known as the delay coordinate, delay plot. Delay plot is where you define a given amount of delay, say from here to here, tau, and plot x t minus tau in the y axis. Now, this delay could be advanced or backward, both. The difference between the two is what really matters, which is tau. Okay. If this is a periodic waveform, say it had been, suppose like this, what will be the result of the delayed thing? It will actually be like this, which means that this is generated from a two-dimensional system with a closed loop that is clearly seen the moment you make a delay plot. You might ask, how much should I take tau? It does not really matter mathematically, because whatever the tau, the topological character of the orbit that you get on this 2D plane will be the same. Topological character of the orbit will remain the same. Only if tau is too small, it will be almost like a flat thing, right? And the more you increase tau, it will become more or more roundish. It becomes easily seeable, but mathematically it is still a closed loop, whatever the value of tau. That is why often we set the value of tau simply by visual impression. For different values of tau, we generate a 2D time series, plot it and see whether it looks very nice. Very nice means, what exactly do you mean by very nice? Here there is a point and here there is a point, how far can we distinguish these two? The more it is roundish, the more easily it will be possible for us to distinguish. Then you see, from here up to a point it goes here, from here up to a point it comes here, we can distinguish. Then in the absence of the exact equation, how do we really do the prediction? This is often done by simply analogy. Analogy means if the state were here, there is a large time series available, so essentially you have something like this, right? If you go on plotting, it will be something like this. If the state is here, from one of the points, you know that if the state were here, where it went 1 second later, because that is already there in the time series. Then by analogy you can say that if the state now reaches here, 1 second later it will go there, and for that it is necessary to distinguish between all points in the orbit. In order to say from analogy, it is necessary to ensure that all points in the orbit are unique. Okay, be able to carry on for long with this throat. So let me say things somewhat quickly. Suppose after having done this, you end up in a orbit like this. What would you infer? The inference is obviously that here we have a problem, because we said that in order to predict by analogy, we will need to have each point unique. This point is not unique, right? This is a crossover. So we need to do something in order to remove this crossing. Logically it cannot have this crossing. So we had generated the time series by saying that one is x of t, this is one set of data, that is what we had started with. Then we said that x t minus tau is another set of data generating this. The moment you have an intersection, you know that you need to increase the number of coordinates that you generate. So you do it as another set of data, which means what are you doing? We have got suppose you have got a data file in which xt are plotted, xt are given. So here will be one line here, another here, another here, another here, so on and so forth. This is x at time 0, time at the next observation instant here. For example, if this is generated by some kind of a data acquisition card, then this time difference relates to the speed of the data acquisition card. Okay. And suppose we have identified tau as 4 lengths of this. So this is as tau, suppose. Then what we will do? We will put this point here, the next point there, the next point there, and so forth. Thereby generate a time series and plot. Similarly here, the moment we do that, this no longer remains a crossover point. This no longer remains a crossover point. Or in other words, if it even after doing so, if it is a crossover, by slight tiny perturbation you can eliminate the crossing. So essentially these become two distinctly different points, and therefore by using the same analogy technique, you can from the time series itself obtain sufficient information to be able to predict what is going to happen. Clear? Now there is an important message here. The important message is that the system itself may be an 8-dimensional system. You are representing it in 3D. What is the guarantee that it is a useful, meaningful representation? That is a serious theoretical question. Is it a meaningful representation? It would be a meaningful representation if somehow we could prove that for each point in the original 8-dimensional orbit, there would be a unique point in this orbit. Then only it would be mathematically meaningful. Is that right? Let me repeat again. I cannot really draw a 8-dimensional thing. So, try to understand. The actual system is 8-dimensional, say. That means at every instant 8 state variables are being generated, and you might imagine some kind of a orbit going on in the 8-dimensional state space which is undrawable. But now we have drawn something by accessing only one state variable out of that. Out of all the 8, we have just taken one data, and we have generated a state space, something like a fictitious state space by this delay coordinate method. Is it useful? There exists a theorem due to Takens which says that yes, so long as the object that you are trying to represent, in this case a one-dimensional object, so long as the object that you are trying to represent is say n-dimensional, if you are drawing just a curve, it is one-dimensional object, okay. But you might also like to draw a two-dimensional manifold or a whole attractor. Whole attractor means what is the dimension of that object? It will be fractal dimension. It will be a fractal dimension. But suppose that whatever it is, that dimension is n of the object. If you choose a number of time series like this of dimension 2n plus 1, then the theorem guarantees that each point maps into a unique point, which means that if you are just trying to represent a orbit is a one-dimensional thing, then you need just 3 dimensions. If you plot it in 3 dimensions, that means you generate 3 time series is sufficient. If you want to generate a unique surface means 2D thing, then you need 5 dimensions at least. If there is a chaotic attractor, which means the attractor has a dimension, suppose you have measured the dimension and you have found that to be 2.8. Then what is the minimum dimension you need in order to represent that in this delay coordinate method? Well, wait, 2.8 means twice n. It has to be, okay, let me put it this way, plus 1 is minimum, it has to be greater than twice n. 2.8, which means its twice is 5.6. Yes, the number, the whole number greater than that is 6. 6 is sufficient. Which means this technique by which you generate pseudo time series, which actually does represent the real thing, in the sense that if the real thing becomes a periodic orbit, you also get a periodic orbit here. If the real orbit is period 2, you also get a period 2 orbit here. If the orbit is period 3, you also get a period 3 orbit here. If your orbit is quasi-periodic, you also get a quasi-periodic orbit here. Chaotic, also you get chaotic. Means the exact property of the orbit is uniquely represented by means of this. This is called delay coordinate embedding. This is called delay coordinate embedding, and the dimension that you need in the minimum to represent that particular dynamical system is called the embedding dimension. It may not be, it is not the same as the actual dimension of the system. This means the minimum number of dimensions that you need in order to properly represent the dynamics of the system. Okay. It will be a nice exercise for you, those of you who have obtained the Lorentz systems, you have the equations and you also obtained the orbit, right? This orbit. This kind of orbit you have obtained. Now, the way to test what I have just said is this orbit, if you have generated it in MATLAB and plotted, there was a stage in which you have obtained the generated the time series and then given the plot statement, right. After you have generated the time series, simply eliminate the vector 2 and vector 3, retain only the first vector. What you have obtained? This is a 3D plot. So, you have x, y and z. X had these numbers coming, y had these numbers coming and z had. That is what you plotted here, right. Suppose you eliminate these and keep only this. Now, choose a delay. How much should the delay be? It's not difficult to see. That should be of the same order of magnitude as the period of rotation of these, that you can easily identify and accordingly choose the amount of delay. If it is too short in comparison to the period of rotation, it will be almost like a very thin thing along the 45-degree line. No, in the Lorentz model you had. No, Lorentz model did not relate to voltages. Lorentz model was atmospheric convection model. You are talking about probably the Chua circuit. Chua circuit, fine, no problem. So you had the differential equations available to you, solve it, and you can always plot the behavior as something like this. In case of the Chua circuit, it is a double scroll like this. It will come like that, fine, no problem. This is actually a 3-dimensional system. There are 2 capacitors, capacitor voltages and 1 inductor, inductor current. So, these are x, y and z. So, x variable Vc1, y variable Vc2, z variable IL, there is only one L. Generate that and eliminate that, keep only this. Now, give a suitably chosen tau, the delay length. Suitably chosen means you might play with it, no problem. I take 10 steps as my tau, let us see what happens. Take 50 steps, let us see what happens. Take 100 steps, let us see what happens. Essentially, that will be related to, you have to take a tau that is of the same order of magnitude as the period of rotation around these lobes or here. Then if you do this, that means you regenerate y and z by means the delay coordinate and then plot it, then you will be able to convince yourself that it really generates the same orbit, not exactly the same orbit, but topologically the same orbit. And if your problem is to identify when a bifurcation occurs, when a period 2 to period 4 changeover happens, obviously this suffices, because the periodicity is retained. You might, having obtained the just from 1, having obtained the continuous time state space, you might place a Poincare section, you might obtain a discrete type description, no problem, yes, you can do that. In fact, a large number of experiments have been done in which the bifurcation diagram has been obtained by this. Simply take one state variable, obtain the continuous time dynamics by delay coordinate plot, place a Poincare section, obtain the discrete time description, and then on that basis plot the bifurcation diagram. that is how most of the experimental work in this field, in the field of nonlinear dynamics, is done. Because in most cases, unlike the cases in electronic circuits where you have 2 variables, 3 variables, easily identifiable variables, in most practical system it is not, and there the delay coordinate plotting is absolutely a must. Okay. Let us stop here, my throat is not allowing.